Alrighty, this is going on page 72 when we're done. This lesson is titled Inverses of Exponential Functions. What are the inverses of exponential functions? Logs, exactly. Okay. So we're going to look at logs and exponentials together. So just as we can graph everything else we've talked about, we can also graph logs. Here's your general form of a log function. The A right here does the same thing the A does in all of them. That is your vertical dilation, your vertical stretch or compression, okay? That B there, that is the base of the log. I think we already understand that. Bless you. B has to be greater than 0. That means you cannot have a negative base and you can't have a base that is 0. B can't be 1 either, because if you think about, if we rewrote this, if I ignore the A and I rewrote it in exponential form, I'd have b to the y power equals x. So the base of the log is the base of the exponential. Your base of an exponential can't be 1, because 1 to the x power, you're going to get 1 every time, right? So it just doesn't make any sense to be a log then. And a cannot be 0, because then the whole thing is 0. So I think sometimes, and remember, it is important that you understand that when you look at this stuff, that you can try and figure out a way to make it make sense to you. Because when you get to college, you could have to be reading some of this stuff on your own, and you don't want that stuff to freak you out when it's really not that bad, right? Just figure out what it's trying to say to you. Because all this stuff right here is basically just telling you that weird things aren't going to happen, okay? All right, so then it says, because exponential functions and logarithmic functions are inverses of each other, we would expect the characteristics of the input-output values of an exponential to become the characteristics of the output-input values of a log function. So just like any inverse, x and y switch places. That's how we make the inverse. So when we did inverses last semester, we had an original function. We could find the domain and range. Then we found the inverse. And when we found the inverse, we would just take domain and range and switch those. So that's kind of what it means by the characteristics. All the inputs become the outputs and vice versa. So let's look at what that means for our tables of values when we're trying to determine what type of functions we have. So this says recall. We're going to go back to what we talked about with exponentials. For exponential functions over equal width input value intervals, the output values change multiplicatively. Okay, fancy word to say we're multiplying by a number, like it's doubling every time, or we multiply by 3 every time, whatever. So it says, notice how the input values, which are x, are changing additively. So here, my input values, I would be adding 2 each time. So that changing additively and equally spaced, are formal words for that are equal length input value intervals. Okay, those equal length input value intervals are very important to us, because if that's happening, then we care about the patterns we would see in the output values. So input values are equal length, while the output values are changing multiplicatively. So here, when I go to each one of them, each time they're being multiplied by 2. If this is the type of pattern you see in your tables, that is indicative of an exponential function, right? That's something that we've already looked at and determined. That's how we know that it's exponential. Okay? Yes, ma'am. Equal length. Oh, it says equal width. Okay, I'm glad you pointed that out. No, there is not, and thank you for saying that. The language that, and one of the reasons we're writing this, because you're not going to have to, we're going to write out a bunch of stuff at the bottom. You're not going to have to write it as an explanation on the AP exam. It would be a multiple choice question. And the wording could vary just a little bit. So that is a very good question. Whether you say equal length or equal width, it really does mean the same thing, even though we've used, they're basically, what it's basically saying is that it's equally spaced no matter what you call it. But the language that we've seen from College Board, it doesn't say equally spaced, and it doesn't say changing additively. It just says, and I feel like, and because addressed this earlier today too. I need to go back and reread some of those questions that came, because we have material that came from College Board and we have material that comes from some other people that are good at writing this stuff. And I like to pay way better attention to the stuff from College Board with specific words, but they do mean the same thing. And as when we get down to the bottom, I'll tell you even what we wrote last year, because last year at this point, we only had one mock exam to look at. And that mock exam had been written the middle of the year prior, before AP Pre-Cal really existed. So it was kind of like, hey, this is what we think we're going towards. And then shortly after this, we got 2 more mock exams where we could really see the language and how it's written there. So I'm going to make you write it for, on here, on your assignment, probably on a test, because the more you see it and the more you write it, the more that when you get to it and you read it, you won't get lost in the wordy words, because some of these answer choices are very wordy. And if you read them quickly, they sound exactly the same when they're not. So I want you to recognize those words. I want you to think about the things that this says length and this says width, and does that mean the same thing? So in this case, it absolutely does. Also not calling them X and Y, but talking about them as input and output. Okay, because that again is more the formal language that you will see. Okay, does that help? Okay, good question. So yes, they're the same thing. And I wrote equal length because that's what I've seen the most, and I did notice it said equal width. But again, this was not written by College Board. It was written by somebody that I would totally trust to write anything for me. But we also are saying things like X and additively. So just getting there, but good question. All right. So then for logarithmic functions, so that other one was the recall, right? These 2 properties of input and output are reversed, because that's what happens with inverses, and they are inverses of each other. So here, when I look at my inputs, I'm not adding 2 every time. I'm multiplying by 2. So my inputs are changing multiplicatively. So inputs changing multiplicatively. And then the outputs, I'm adding 2 each time. So they are changing additively. They are equally spaced. We would write this as equal length output value intervals. Okay. And when this happens, you can see it's just literally reversed from what it was for the exponential. That's indicative of a log function. Okay. So we know how to identify linear, quadratic, really any polynomial, because we can do the differences, and then now exponential and logs from a table. But this one is just asking us to decide if it is logarithmic, exponential, or neither. So if it doesn't fit one of those 2, then our answer is just going to be neither here. Bless you. So when I look at my input values here, we are adding 1 each time. When I look at my output values, it looks like we're dividing by 2, but remember we talk about it being multiplicative, which means I'm actually multiplying by 1/2. It's a multiplicative change, not a division change. So since my inputs are equally spaced and my outputs are changing, being multiplied by 1/2, what does that make this? Exponential, logarithmic, or neither? Exponential. This is how we recognize an exponential, okay? So exponential, and here is our explanation. We have equal length or width, input value intervals, okay, so that's the first part of that. And then our output values, are multiplied, and you can abbreviate multiplied, by 1/2. So you don't have to say that they change multiplicatively, but you can just say what they're being multiplied by. But for the additive, I don't know. I mean, you're not going to see it as we're adding 1 each time. That's not the wording you're going to see there. You're going to see something like equal length input value intervals. Okay. What questions we got? Awesome. All right, so let's look at B. When I look at my X values, so it looks like I would add 20, add 30. Well, that's definitely not changing by being added, but if I multiply by 3, by 3, by 3, so times 3, right? Then when I look over here, looks like I am adding 10 each time. So my output values are changing additively. My inputs are changing multiplicatively. What does that make this? Logarithmic. Good. And you can just say log, and that's fine too. As long as you know it means logarithmic, it's fine with me. So then I would say that my input values are multiplied by 3. Okay. And then I have equal length output value intervals. And if you talked about the outputs first, if you said I have equal length output value intervals and then the input values are multiplied by 3, that'd be totally fine. As long as you say it all, then it doesn't matter how you write it. What questions do we have? We all good so far? All right, so then C, look at this. Looks like I'm multiplying by 10 each time. Yes. Here, looks like I'm multiplying by 2 each time. Okay. So what do you think it is? Logarithmic, exponential, or neither? Neither. So we can say neither input values multiplied by 10 output values multiplied by 2. Any questions at all at this point? All right, so then on D, what's happening with my input values? Times 2, yes. My output values, well, they're, yes, minus 3, but if we're changing additively, we're actually like adding a negative 3. Does that make sense? Okay, so is this logarithmic, exponential, or neither? Logarithmic. So you go ahead and write out your explanation. You have something to follow over there. Input values are multiplied by 2, and we have equal length output value intervals. Any questions at all? Ask me a question, Rachel? You have a question? I don't know why it looked like you were about to ask me a question, but no? Okay. All right. So exponential and logarithmic functions as inverses. So in general for inverses, having nothing to do with exponentials and logs, we know that if we do f of g of x and it's equal to g of f of x and they're both equal to x, that's what makes them inverses. That's how we verify it, okay? And then, so if f of x equals b to the x and g of x equals log base b of x, then f and g are inverse functions. Okay, so basically if they both have the same base and they both have the same argument, okay, so b to the x or log base b of x would be inverses of each other. Two important properties just in general of inverses is that graphs of the inverse functions are reflections over the line y equals x. That's your parent function for a line. Graphically, that's what's happening. Visually, that's what's happening. Also, if x1, y1 is on f, then y1, x1 is on f inverse, because that's how you do an inverse, right? Your x and your y's switch places. Okay. All right. So on example 2, we are going to show that f and g are inverse functions. If I'm being asked to show it, they're not asking me if they are. They are saying, these are inverse functions, show me that they are. So it's not a yes or no type question. And they're telling me to find f of g of x and g of f of x. So when I do f of g of x, this is g, I'm going to take that and substitute that right there where x is. Casey, you with us? So that means I'm going to get 3 to the log base 3 of x power. Now, we have not reviewed our log properties and our log manipulations yet, which is probably a good thing because then we don't have to get this all mixed up with all the rest. There is a mathematical reason behind why what I'm about to tell you is true, and we will look at that once we review what our steps and stuff are. But if you have an exponential that has a log in the exponent, and the base of the exponential and the base of the log are the same, they, in a sense, cancel each other out, and you are left with whatever the argument is for the log. So 3 to the log base 3 of x power is literally just x. Okay? So if the base of the log and the base of the exponential match like that, you just get x out. Now, it doesn't just magically jump out of there. Like I said, I'll show you the math behind it a little bit later. But I do want to point out that something like this came up in calculus either yesterday or the day before, because Ackerman came out telling me about what went on in his class. And they had something like, well, they had e to the natural log of x power. And I don't even remember what he said they were doing, whether they're integrating or taking a derivative, but it doesn't matter because you don't know what those things mean anyway. But they were having to use this. And if we took that and like put it in as it is, it was going to make whatever they were doing really complicated. So their little wheels were turning about, how am I even going to approach this? But then somebody was like, wait a minute. What is the base of the natural log? E. So the base of the natural log matches the base of the exponential. So this just equals x. And when they were going to do whatever they were going to do with just x, it was a piece of cake. Okay? So I'm saying that to say this stuff is not going away. Those are things that sometimes we get things that look super complicated, but when we simplify them, they're actually very simple. All right? But that works for a natural log, works for a log base anything. Okay? We good on that? All right, so then I'm going to do g of f of x, which means I take this and substitute it in for x right there. So then I'll get log base 3 of 3 to the x power. So this time, instead of a log being inside of an exponential, I have an exponential inside of a log, but the base of the log and the base of the exponential match again, which again, in a sense, they then cancel each other out, and you are just left with x. But it's no magic that it just jumped out of the exponent. I feel like I can show you this because I know these aren't brand new to you without this blowing your mind, and you might remember some stuff from logs. But if I have log base 3 of 3 to the x, regardless of whether or not those were 3's or whatever they are, if I take the log of something with an exponent, one of the rules we have is that the exponent gets to come out front. And this gives me x times log base 3 of 3. Okay, do y'all remember that rule? And so since that happens, what's really happening when it cancels out is that if you take log base 3 of 3 or log base 5 of 5 or log base monkey of a monkey, whatever, this is always going to give you 1, so you have x times 1, which is just x. So that's how that's happening. It's no just willy-nilly magic. There's steps involved there. It is magic. We good so far? Yes? All right, good deal. All right, so here we have a portion of the graph of the exponential function 2 to the x power graphed for us. So this is 2 to the x. This line is y equals x. Okay? And we want to sketch the picture of k inverse of x, which would be the log. So 2 to the x power, the inverse is log base 2 of x. That's the way the inverses work. It is very helpful for you to understand how these things work graphically. Now, we don't do a whole lot of actually plotting points and graphing this stuff because where the actual points are sometimes don't matter to us. But it is very important that you have a visual in your mind of what an exponential looks like. So if you know you have k of x equals 2 to the x, then you should know that basically it's going to look like that. That's the parent function. There's no transformations or anything. Not only does it look like that, but you have an asymptote right here. Because another thing that comes up sometimes in here, sometimes in calculus, is you figuring out when this is going to be equal to 0. Well, if I have an asymptote right there, it's never going to be equal to 0. I don't have to do any math. I don't have to do anything. If I know that's what the parent function looks like, it tells me that right there. Okay. Also, regardless of the base, whether it's 2 to the x, 5 to the x, a million to the x, anything to the x, 0 power is 1, right? So if I have no transformations, then when x is 0, y is 1 right there every single time. So it's going through 0, 1 if I have no transformations. That's an important thing to be able to keep straight in your head as well. So then we're also going to be able to have just a general parent function of k inverse of x, which is log base 2 of x. Okay, we'll get there in just a second. But we know that this point here is at 0, 1. So then the inverse, I flip the 0 and the 1, and I get 1, 0. And I get that point right there. And really, that's probably enough for me to get what I need, but we're going to go ahead and get 2 other points so that you know how to find them. I have this point right here, which I can see is 1, 2. So that means for my other graph, I'd have 1 at 2, 1. Then I have -1, and then whatever that point right there is. Well, what is 2 to the -1 power? 1/2, right? So that means that this ordered pair right here is -1, 1/2. So I can go to 1/2, -1, and get a third point there. Okay, everybody okay with that? Then since I have a horizontal, to make that smaller. Since I have a horizontal asymptote right here, oh, I accidentally erased my point. Sorry, hang on. There we go. Since I have a horizontal asymptote right there, when I reflect it, I end up with a vertical asymptote right here for my log. So my log function looks like this. So for just a quick parent function sketch or a picture in my head, it looks like this. That right there is going to be at 1. Okay. So what that tells me is that log base 2 of 1 equals 0. Because when I plug 1 into here, I get 0. Any base, the log of 1 is going to give you 0. Let's say this was log base 50 of 1. If I was to rewrite that, I'd have 50 to the 0 power equals 1. Okay, and that's why it works, because you have 2 to the 0 power equals 1. We're basically just rewriting these in the different forms. Okay, so we know that that's happening with the 1 and that we have an asymptote here. And that means, what do you think I would get if I tried to take the log of 0? Undefined. If I substitute in 0, I'm not going to get a number out, right? Log of 0 is undefined. You can't take the log of 0 no matter what base you're in. And we know that for sure because of our asymptote, okay? So knowing some properties, and sometimes if you can't keep the properties straight, being able to do a little quick sketch can help you with all the properties and where things go. Okay? What questions we got? All right, good deal. So this last one says, the exponential function h of x equals a to the x contains these 2 points. We want to find the average rate of change of y equals log base a of x over this interval. All right, well, if this is h of x and it's a to the x power, and this is log base a of x, that means this right here is h inverse of x. Okay? And it's asking me to find average rate of change. What is the average rate of change? Slope. Okay? So if I want the slope of h inverse of x over this interval, then that means I'm going to have h inverse of 27 minus h inverse of 3 over 27 minus 3. I should be able to set that up without wondering where anything else comes from. All 4 of those numbers there came from that interval, and then the function's name was h inverse. That gives me my function notation, puts everything in there where it's supposed to be. Now I need, what they gave me were ordered pairs for h of x. I need ordered pairs for h inverse. So I switch x and y. This, I'd have 3, 2 and 27, 6, because I'm just switching x and y for those, right? So if I substitute 27 is my input for h inverse, what is my output? What's h inverse of 27? 6. So this is going to give me 6 minus h inverse of 3 is 2 over 27 minus 3, which is 24. Gives me 4 over 24, which reduces to what? 1/6. Not 6, 1/6. I see it too much when I know you know what you're doing, but you end up putting something like 6, because your brain's thinking, oh, 24 divided by 4 is 6, which is totally a true statement. Just make sure you put the 6 in the right spot. Okay? What questions do you have? Okay. On your assignment down at the bottom, it says, use the graph above to approximate the following values. That means literally approximate. You're estimating. And I know you kind of, what was that? Am I hearing things? I know sometimes you're afraid to like estimate and come up with numbers because you feel like you're guessing. It's asking you to just do your best to guess, okay?